schemes of realizing matching, reflection match with single transistor circuits, and we did not really consider how to bias them. We saw three topologies. One was common source amplifier, one was the common gate configuration, another one also a single transistor with a feedback around it. So the goal in today's lecture, part of the goal in today's lecture is to also show you how to bias these topologies, right? And then maybe talk about noise if time permits. Okay. So let's start. So let me start off with taking. I mean, I can choose any one of the three, but um, let me just start off with the common gate topology that we used for matching purposes, right? So our antenna is mimicked by this input and a 50 ohm load or 50 ohm source resistance. You have this transmission line. Again, you must recall that there is probably a SAW filter, SAW filter upfront, which we are not capturing in this schematic. And this was the small signal model of the common gate amplifier or the common gate input stage, and we saw that the input resistance here is approximately equal to 1 over Gm plus Rd by intrinsic gain of the transistor M1. Okay, all we have to do is to ensure that this is equal to R, then we have a match, right? So given that we need this type of configuration, and noting that this is only a small signal model, and the next thing is to this is a small signal representation. The next thing is to put the bells and the whistles around it and ensure that the transistor is actually biased properly, right? Okay, so let's go ahead with the biasing scheme. So firstly, let me just sketch out a common gate configuration. So firstly, we know that there has to be a supply, right? That's for sure. The gate to source voltage has to be biased in such a way that the transistor is actually turned on with certain amount of Gm, right? So which means that in this case, since the gate is incrementally grounded, so incrementally grounded essentially means that I can add a battery directly. So let's say I add a battery. Okay. What else? What about the source side? Now note that the source side, I cannot really ground it because the source has to go into the transmission line, right, at the transmission line end. And what is the, so if I only consider the transmission line end, right, so what is the quiescent voltage at this point? The quiescent voltage at that point is essentially zero, right, because we are connecting everything to the antenna, and this is mimicking a sinusoidal source which has a zero DC level. So if there is no DC connected anywhere on the circuit, on the part of the circuit on the left, then essentially it is at a zero quiescent point. Now one might say that zero quiescent point is essentially good, because if this point, if the gate of the transistor is biased with a VG and the source has a zero quiescent point, that probably is the best case scenario, because I can have a sufficient amount of VGS to keep the voltage turned on, keep the device turned on, and I can also provide the incremental inputs, right? But the issue with that is we expect the signal to swing here, right? If the input swings, right? If the input swings, if this swings by uh, dpp, that is peak to peak voltage, how much do we expect the swing here? Here we expect the swing by vpp by 2, right? So what's the problem with that? The problem with that is if we go back to our again, I'd like to take you back to your undergraduate days of a cross section of a MOSFET. What does a cross section of a MOSFET look like if it's an NMOS transistor? So this is an oxide, and on top of that you have a metal or a polysilicon, and you have doping here. If this is the NMOS transistor, then you have a P minus body, you have N plus here, you have N plus here. This is biased, and let's say this is uh, uh, so your body is connected to ground. Okay, now let's say this is the source terminal. Okay, so and we are saying the source terminal is swinging. Okay, so if the source terminal has a quiescent ground voltage potential, that is you have a source terminal to be 0 quiescent wise, then what happens when you have a negative portion of the sinusoid? So when you have a negative portion of the sinusoid, the N plus doping stage, the N plus doping terminal actually goes negative, right? So what happens to the PN junction here? Note that you have a PN junction here. Right? You have a PN junction here, and when the N plus quiescent voltage or the N plus terminal starts to go negative with respect to the body bias, then the PN junction starts to turn on. It doesn't immediately turn on, but it starts to turn on, and this diode starts to conduct. So the current that was supposed to flow in the channel, right? The current that was supposed to flow in the channel doesn't flow into the channel. It now gets diverted to the diode, so you do not essentially get any voltage, right? So you essentially do not get what you want, because now what is going to happen is there is a third terminal, which is a body terminal, which is grounded, and if the body terminal and this source gets forward biased, right? So essentially you have a diode between the source and the body. If the body and the source terminal starts to get forward bias, when the source goes negative around this side, then obviously the current will go into the body and it will not go into the drain, right? So that's a loss. So you would never want this to happen. If you never want this to happen, then what measures should we take? We should ensure that the source is not connected to ground, not physically connected to ground. Okay, so then what are the possibilities? So what is the key takeaway? Ensure source is not connected to ground when the source terminal is swinging, is expected to swing. Okay, is not connected to quiescent ground, right? I should say is source terminal. Ensure the source does not have quiescent ground potential when the source terminal is expected to swing. Okay. Okay. So how do we start off biasing? By the way, how do we bias any common gate amplifier? In our basic analog circuit courses, we have seen the way to bias a common gate amplifier. The general way to bias is to put a current source at the source terminal, right? And one might also want to put a resistor. This is another way of biasing, right? Either of them will be able to uh, bias the transistor, provided you have appropriately chosen the values of the current source, the resistors, uh, and the gate voltages. But which one would we prefer? Normally, we tend to prefer this one. I mean, analog circuit designers tend to prefer this topology because it fixes the current in the stack. Moment you fix the current in the stack, then there is a then we more or less have an idea of what the GM of the transistor will be. And because in our case also the GM is essential, the value of the GM is essential, it becomes important to understand what the value of it becomes essential to ensure that the matching is honored, right? But regardless of whether you choose this topology or this topology or any other topology, the stuff that we need to be aware of is the fact that the input is getting attached here, right? The input is getting attached here. So how do we couple the input? That's the question, right? So how do we couple the input? So let's say now I connect, this is DTD, and let's say I have a current source here. Okay, so I call this I naught, and our signal is coming. I'll draw the transmission line for once now, and after that I will drop it. I will assume that you understand there is a transmission line. Now if I connect it directly here, what's the problem? Clearly the problem is the quiescent point of the transistor is going to get affected. So that is why we do not do this. That's why. But fortunately, we know that. Fortunately, in our case, we understand that everything is operating at not at DC, but at a fairly high frequency away from DC, probably hundreds of megahertz or few gigahertz. So essentially, we can AC couple. We can put a capacitor, a coupling capacitor, right? We can put a coupling capacitor here, or you might want to say a DC blocking capacitor. Let me just call this C1. So this is a DC blocking capacitor or a coupling capacitor, right? Uh, which couples the input to the source, right? So if I have to, the next thing is how do I know how do I decide on the value of the capacitor? So how do I decide on the value of any capacitor when I have to uh, pass certain signal of a frequency and not and prevent the DC to go through? For example, what happens if how do I know how to decide on the value of this capacitor? Let's say I call this R1, I call this R2, and I call this C. So how do I decide the value of this capacitor C so that the current so that it acts as a short circuit to the frequency of interest and blocks the DC? I mean, it obviously blocks the DC, but I would expect this capacitor to act as a short circuit for the frequency of interest. So again, uh, so essentially, what we are interested in is to ensure that the impedance of the capacitor is much lesser than the is much lesser than all the resistance associated around the capacitor, right? So ensure impedance of the capacitor, that is 1 by j omega c, or in this case mod of 1 over j omega c, is much less than the resistance associated with the with that loop, right? So Thevenin resistance around it, right? So another way of expressing the same thing, I mean, let me just complete this, then I will talk about the other way. So what I am essentially saying is an omega 1 over omega c should be much less than r1 plus r2 in this case. So i.e. the time constant associated with the capacitor, which is c times r1 plus r2, has to be much less greater than 1 over the frequency of interest, right? So in other words, the time constant should be much greater than 1 over omega, right? So that's what we would like to ensure. So what is the time constant around the capacitor in this case, in our case? So if I if I say this is the capacitor, so what is the loop around the capacitor? So what is the impedance looking up? If it is matched, this is impedance is R, right? So this is R. What is the impedance looking to the left? That obviously is again R, right? So what is the impedance around C1? By the way, how do I find out the impedance? In order to find out the impedance, I short the input. I know that this side is also R, this is R, this is Z naught, which is equal to R. So the looking this side is R, looking this side is R. So essentially this is C1 with 2R. So the time constant is 2R times C. So I have to choose the value of the capacitor such that 2R times C1 is much greater than 1 over omega, where omega is the frequency of interest, which essentially means that C1 should be much greater than 1 by 2R times omega. Okay, fine. So we have found out the value of C1. That's good. How do I choose the value of I naught? If this is a long channel device, if I neglect channel length modulation, my IDS is equal to half mu n C ox W by L VGS minus VTH whole square. This is for long channel. And neglecting channel length modulation. Okay, which essentially means that your GM, I can write it as under root 2 mu n C ox W by L ID, which is in this case equal to I naught. Now again note that I could have written any other form of GM, but that wouldn't probably have been the right, not probably, that wouldn't have been the right expression, even though mathematically they are all equivalent. The reason I would like to choose this expression for GM is because I know the I naught is constant, right? So choose, so essentially we need to choose I naught and W by L such that GM is approximately equal to 1 by 50 ohm, which is 20 millisiemens. Okay. So now obviously you see that there are infinite possible combinations, because I can choose a very large value of W by L and a very small value of I naught. This equation is basically telling us there are any sort of combination that are useful, right? So now the caveat to this equation is, firstly, it's for long channel device. But even for long channel device, you have to ensure that the transistor is actually on, right? So what happens if I increase I naught? What happens if I keep on increasing? Let's say I want to keep the GM fixed and I want to increase I naught. If I want to keep the GM fixed and I want to increase I naught, it essentially means that uh, I have to reduce W by L. And if I am doing a power constraint design where invariably we would like to ensure that we are not burning more power, we would like to do the reverse. That is, we would like to reduce I naught, right, and naturally increase W by L, right? So, but if I reduce I naught and increase W by L, what happens? So that seems to be a good strategy, right? So to save power, reduce I naught and increase W by L. Correct? So if I reduce I naught and increase W by L, then what happens? Now note that my VGS is essentially, or VGS minus threshold voltage, which we call the overdrive voltage, is essentially under root 2 I naught by un Cox W by L, right? So if I reduce I naught and if I increase W by L, then V overdrive decreases, which essentially means that your transistor is going closer and closer to subthreshold, right? It will never go fully to subthreshold, right? But it will go closer and closer. But as it turns out, if you do that, all I mean, firstly, the problem is that the equation the saturation region equation that we are so familiar with, does not hold anymore. The transistor starts going into subthreshold, and moment the transistor starts going to subthreshold, what generally happens is, uh, you can think of it in this way that if the transistor is not on and you are trying to swing the voltage at the source while keeping the voltage at the gate fixed, then in one half cycle you are trying to push the transistor more into subthreshold. In other half cycle you are trying to make the transistor on, slightly more on, right? So essentially you are going to get different response from the transistor at the positive half cycle and with respect to the negative half cycle, which essentially means that if you give a sinusoidal input, your output current will not be sinusoidal, which means you are going to get some sort of distortion. We'll talk about distortion after we are done with a few more lectures. Uh, but for the time being, it should not be very difficult to understand that when if the transistor characteristics itself is going towards the transistor being turning off, when the signal is swinging in one direction, towards the transistor being turned on when the signal is swinging in the other direction, then obviously the current, the resultant current that is going to come out will be distorted, right? So you cannot play this game very much, so you have to give certain amount of overdrive voltage always, right? And how much overdrive you can keep will be determined by how much of the distortion that a distortion of current that we can tolerate. Okay, so so you have to balance this, right? So the design is it's not very at this stage we are not in a stage to fix the value of I naught and W by L. But having said that, we at least know that I naught times W by L has to be constant and of some value. Okay, okay. Uh, so what else? What do we need to decide on? So let's say I have decided on I naught, I have to decide on W by L. We need to decide on the value of this voltage Vg, right? So this VGQ. How do I decide on the value of the voltage VGQ? So I am not now sketching the entire circuit, I am only sketching this part of the circuit. How do I know what is VGQ? So firstly I have to ensure that this VGQ, whatever voltage I have, is sufficient enough to keep the transistor on, right? So essentially when I say that, what does VGQ set? If the transistor is in saturation, I know that this voltage is VGQ minus 1 VGS when the current through the transistor is equal to I naught, which is nothing but VGQ minus what is the VGS? 1 threshold voltage plus 2 I naught by mu n Cox W by L, right? Or other words, other way of writing the same thing is, the more popular way of writing the same thing is VGQ minus threshold voltage minus the overdrive, right? So this is the overdrive voltage, right? So essentially this. So so if I take rough values, let's say if threshold voltage is 400 millivolt and overdrive voltage is like 200 millivolt, right? So say threshold voltage is approximately 400 millivolt, V overdrive is approximately 200 millivolt, which are generally the typical numbers typical numbers that you will arrive at later on when you that will arrive at uh, for let's say a 1 volt supply process. Then uh, then you see that the voltage VSQ is essentially VGQ minus 600 millivolt. And if I have to ensure that VSQ is always above 0, VSQ is always above 0 volt, right? So then this has to be greater than 0 volt, but not so fast, because I'll have to ensure that this also takes into account the signal swing. You remember? So we have to ensure that this signal swing on the negative half cycle is also accommodated for, which means that this has to be greater than Vp by 2, right? So we'll have essentially my VGQ has to be greater than 600 millivolt plus Vp by 2 in this particular example, right? So that's always a caveat. Okay. Okay. What else? How do I decide on the value of RD? So clearly, if I have a supply voltage VDD and the current that is getting pushed through RD is I naught, then this voltage is VDD minus I naught times RD. So this definitely has to be, this voltage cannot drop too much, because if it drops below one threshold voltage over VGQ, then you are going to land up into triode region, right? So you are not going to get any gain. So that we have to stay away from. But not only that, this is only for biasing constraint, but we know that we have signal current also, right? What is the signal current that we expect? And if everything is matched, what is the signal current that we expect? When everything is matched, the signal current that I expect is Vi by 2R. This signal current is supposed to flow into the transistor. This is the incremental current that is supposed to flow into the transistor, which means this will be not I naught times RD. So this should be I naught plus Vi by 2R times RD, right? And this is the worst case condition, and this has to be greater than VGQ minus 1 threshold voltage. So, and instead of Vi, you basically replace Vi with the maximum signal swing that you are expecting. So from there, you will have an idea of what value of RD you need, because typically VDD is fixed by the process. Okay. Okay, but we are not done yet, because generally in a circuit you are going to have only one current source, and you cannot keep on putting current sources as sources of every transistor that you encounter. You will have to use that single current source, and then use it as a in the form of a current mirror. So generally the way to go about doing it uh, is this. So you have a current source, and how do I ensure that the same current source is used everywhere? So I am going to use a current mirror. If this is 1 is to 1, then obviously the current I naught is going to get mirrored. If you want to save current in the biasing, then you make it 1 is to n and make this I naught by n. So you are going to see, as long as all transistors are in saturation, let me call it m uh, m0, and let me call this m0 with m a, and I call this m0. Okay, so as long as transistors are in saturation, then you are going to get I naught current in this stack. Okay, couple more things to take care. Yeah, one important thing to take care is how do I get this voltage source? This voltage source, again, you have a one VDD and you derive everything from the VDD. So how do I get that voltage source? So I can get these voltage sources multiple ways. One of the ways is probably this VDD. I call this, say, R1, I call this R2. So your VGQ becomes VDD times R2 by R1 plus R2, right? Okay, but not so fast, because there is an issue with this particular configuration if you are not careful at high frequencies. And the issue is as follows. Note that your signal is getting coupled here, right? Okay. So now, so far, what we have done is we have neglected the parasitic capacitance which exists between these two nodes. So I'm always going to have CGS capacitance between the source and the gate of the transistor. Okay. So if I am going to have this CGS capacitance between the gate, so again, I mean, um, later on when I talk about how to optimize the size of a transistor, right, in the sense that how to optimize the layout of a transistor, we'll talk about, or how to reduce the effects of parasitic capacitances and the sources of these parasitic capacitances. But for the time being, let's go with the fact that there is a CGS capacitance, and that CGS capacitance is going to affect my device performance. Okay, so given that this exists, right, we'll have to come up with a way we have to try and understand what are the potential problems. Okay, so if we have a CGS capacitance, what do we see? Uh, Having many things on the paper might be clumsy. So what I'll try to do is to reduce the circuit to a manageable proportion, and I'll only concentrate on what is happening around M1 in the incremental sense. Okay, so let's concentrate to whatever is happening at M1. So I understand that I have a current source on the bottom, so incrementally that is not required, and I understand that I have a incremental current. I mean, I have an incremental current of Vi by 2R that is flowing in. And now note that incrementally the gate is not shorted anymore, because what is the incremental impedance looking into this resistor stack? The Thevenin impedance is essentially R1 parallel R2, and R1 parallel R2 to ground, right? So we have R1 parallel R2 to ground, and we have this capacitance here. So what happens to this? What is this voltage here now at what is this? What is this voltage here? So if I know, if I am anticipating this voltage in term, at least in terms of Vs, V source, what is this voltage? That voltage is nothing but basically a high pass version the uh, of uh, of the source voltage, right? So that is Vs times j omega Cgs by 1 plus j omega Cgs R1 parallel R2. Okay. So now what happens to this voltage as frequency increases? As this frequency increases, as you can see, the CGS capacitance, the impedance provided by the CGS capacitance reduces, right? The impedance provided by the CGS capacitance reduces, and uh, the gate voltage of that, incrementally the gate voltage of the M1 transistor is also getting shorted to the source voltage, right? So essentially incrementally you are incrementally the transistor is turning off, right? So if you do this, so what's going to happen? So if I plot this with respect to frequency, with respect to omega, I'm going to see something like mod of Vg over Vs. I'm going to see something like this, and this will go to 1 at high frequency. Now, if whatever is a high frequency is your matter of interest, then at these frequencies, right? So if let's say this is your omega naught where you are trying to operate your circuit at, then at this frequency, what are you going to see? You are going to see the VGS has shut down. If the VGS has shut down, right, and then the GM VGS is also 0, so the incremental impedance that you are going to see is going to increase, right? Uh, or in other words, uh, in in other words, the current that you are trying to push in here, this current that you are trying to push up is essentially Gm times Vsg. If Vsg is tending to 0, the current is reducing. A very good an extension, an extension to this probably is basically to find out what is the effective input impedance of this contraption. I will let you do it as a DIY. So this is R1 parallel R2 CGS. Find out Zin, right? So I'd encourage you to do it yourself to verify that indeed the Zin increases with frequency. Okay, so if that is the case, we have a problem because we anticipated the Zin to be equal to 50 ohm. That's what we biased it at, but it looks like because of the effect of CGS, we are having a problem. So what is the solution? To understand the solution, we have to find out the root cause of the problem, and the root cause we understand is the fact that the gate is not incrementally grounded. I want the gate to be incrementally grounded, but the gate is not incrementally grounded because I have R1 parallel R2 to ground. It's not fully shorted. So one might say the one way to ensure that the gate is a better short is to reduce the value of R1 parallel R2. I can reduce the value of R1 parallel R2, but then what is going to happen is the current that you are going, the biasing current that you are going to draw, that is VDD by R1 plus R2, is going to increase. So you will be unnecessarily burning a lot of power just to bias, right? So what are the ways of incrementally shorting or shorting a node at high frequency that we are familiar with? Again, and going back to our basic analog circuit courses in our UG curriculum, we understand that the easiest way to short a node is basically to incrementally short is to put a large capacitor from that node to ground, right? So, so the solution seems to be that Okay, I have this CGS and I have this. So why don't we take a big bulky capacitor which is much greater than CGS and put it to ground. So at high frequencies, this node will be, so at omega tends to infinity, this node will be what? If this is Vs, this node will be essentially Vs times CGS by CGS plus C2. If C2 is much greater than CGS, then obviously that node voltage is much smaller than Vs, and we have a kind of a incrementally shorted gate, right? Okay, so where are we then? What is the design that we have come up with till now? So we have this, then we have another capacitor C2 to ground, then maybe I naught over n, 1 is to n, this is M1, this is RD, R1, R2, right? C1, right? Okay, okay, fine. Uh, so this seems to be a very rudimentary um, input stage where uh, which I can use to ensure that um, my signal from the antenna that is coming is still matched. Okay, so we note that we have only considered matching till now, and to some extent we have also considered the signal swing, right? We have not considered anything else. There are a lot many other things to consider, but for the time being, we have only considered matching and some amount of signal swing for under the condition that the supply is limited, right? uh, so going forward, uh, from the next lecture onwards, I'm going to change this topology slightly, right? And we are also going to introduce the effect of noise, and then see uh, how this particular topology will start getting modified. Okay, okay, we'll stop. Thank you.